Okay, we've familiarized yourself with the table and the main group names that we want to learn. I don't like the term group. I like family. Alkali metals, alkali earth metals, halogens, noble gases. Why do I prefer family? Like family tree, it tells you it's vertical and they're related. We now have discovered some patterns we've seen on the table. We've noticed that when we do the Lewis dot diagrams, they go in a nice sequence. 1 valence electron, 2, 3, 4, 5, 6, 7, to a full shell over here. Okay? The pattern is not in this region here. So we sort of stay out of there. So if we ignore this big central transition metals, we find this lovely pattern in this block and over here that continues. Obviously, using the valence numbers +1, +2 is a little bit easier than drawing the dots. The full technique, going from the Bohr diagram to the Lewis dot, you have to be able to demonstrate on a test, but after that you can just simply use the valence number stated to give you the dots. So there are 3 ways to get the electron count for the valence shell. Do it this way, all the way from the Bohr to the Lewis dot. Simply count 1 dot, 2, 3, 4, 5, 6, 7, 8, or read the valence number, like zinc will say +2, 2 dots. So you have 3 different ways of getting the answer in order to move on. Now I've stripped the table down to just the part we want to work with. We don't need the noble gases on the right because they do not participate in chemistry. Doesn't mean they aren't useful. They're incredibly important, but largely because they have no chemistry. They're great inert material for protecting things. The ones we are interested in are the metals on the left and the non-metals on the right, and to see how they will interact. I've also kept iron and tin in here because they're really useful metals as well. Osmium, kept that on there because it's the densest metal in existence, and it was actually named after Ozzy Osbourne the rock star because he's a really dense, heavy metal character. So it's a little known fact about the table people are not aware of. So what we're going to do is look at how do we get these guys on the left to react to the ones on the right, and will the Lewis dot diagram predict that for us? Okay, here's where color coding comes in. I'm going to make a very common chemical, the one that's in your stomach, hydrochloric acid. So we take hydrogen and we draw its Lewis dot. 1 dot. Then we'll do chlorine, which has, over here, 7 dots. What I'm going to encourage you to do is draw the empty and make it face towards the element it's going to bond to. Again, the empty is not normal notation. So what's going to happen? These both have equal number of protons and electrons, but nature dictates that there be a symmetry between their valence shells. So hydrogen can sit there and park its valence electron into chlorine, and that makes it look like hydrogen has an empty shell and chlorine has a full one. So they've succeeded in getting a symmetry between them that they couldn't do on their own. If we bring them closer together, it becomes more obvious. Put the hydrogen here. I'll put his electron there. Put the chlorine here, and I'll put its 7 electrons around it. From your viewpoint here, if I hadn't color-coded these, it looks like there are 8 necklacing chlorine and none around hydrogen. This is called an ionic bond because the hydrogen gave up an electron, hydrogen now has a charge of +1. Because chlorine accepted an electron, it has a charge of -1. We can do this anywhere on the table. If we decided to get beryllium here, which is listed as having a charge of +2. So it has 2 valence electrons. If it was going to react with chlorine, chlorine comes down, put her empty. Looks like beryllium can park an electron there. However, beryllium still has 1 to empty out of its orbit. The solution is obvious. Bring in another chlorine, and we can complete the reaction. So, if beryllium and chlorine react, what would form is 1 beryllium marries 2 chlorines, and that is the formula for beryllium chloride. Unfortunately, we can't prove that these formulas actually work. All we can do is show you the technique, and then one day you'll be able to do experiments that prove that hydrogen and chlorine, it's 1 to 1, but beryllium and chlorine, it's 1 to 2. This is how they were able to predict the formulas that they were actually seeing in reality. So we'll take a look at another example involving iron and tin. All right, iron is listed on your atomic table as having +2 or +3. What does that mean? It means iron can show up like this, or iron can show up like that. What happens if iron is going to react with bromine, which says -1, which means all but 1. How many are you going to need to interact these two? Well, I think it's pretty obvious. If you draw bromine here, put the 2 empties there, and fill in your other 7, you can see, put the X at the destination, that this would be iron and 2 bromines. And similarly, on the lower one, I think it becomes pretty obvious. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And here comes the completion. The 8th one, the 8th one, the 8th one. This form of iron would be iron trichloride. Now I switched, without paying attention, that I switched to chlorine, but it wouldn't matter. Chlorine and bromine look exactly the same. 7 dots, 1 missing. Now, let's see what you brush your teeth with. If you turn over your tube of toothpaste at home, it will say you are brushing your teeth with tin 4 fluoride. What does this 4 mean? Well, if you look on your valence chart in your textbook, because you cannot draw a tin, it's well beyond element 21, you cannot go from the board to the Lewis dot diagram. You just simply have to look it up on your chart. +2, +4 are the options. When they write the name of the chemical out, that Roman numeral 4 is telling you right off the bat, this one. You don't even need an atomic table. So the tin that they are using in your toothpaste looks like this. 4 valence electrons. It meets fluorine, which is -1, which means loosely all but 1. So fluorine's going to gain an electron, and tin wants to lose 4 electrons. So how many fluorines do you think this is going to take to pull that off? Well, it's pretty obvious that it's 4. And this is why I've encouraged you to be neat. Because if you draw it neatly, it makes sense that you're going to get the answer of tin fluoride like that. This is what happens if you're not neat. How am I supposed to mark this? I don't expect you to take half an hour with every one of these, but if you're a little bit neater, it's not just that I can't mark this. You'll probably get lost halfway through if you don't try for at least some organization so you see this clearly. So this is how you would set up Lewis dot diagrams when you're asked to lay them out for me on a test. This sheet here gives you great detail. It's a full lesson. Everything you need to know about this is on here. You should keep it for grade 10 as well. So read through this sheet. It summarizes what I just did. Now here's your assignment. How to predict compounds with Lewis dot diagrams. There's the repeat of the lesson, plus a little bit on how these things are actually named. So please read this section right in here that explains what happens to the words when these compounds get together and marry. So your instructions here are to put your Lewis dot diagram of your first element, like that. The Lewis dot of the second element. Always face the full and the empty towards each other to make the diagram simpler. If you don't, the diagram becomes a nightmare. So you draw this guy here. You draw the one he's planning to react with. An egg carton that's almost full meets an egg carton that's almost empty. They will pass the electron this way. The complete formula would be KCl, and it is pronounced as potassium chloride, not chlorine. That's what this lesson for is right here. So you just go through this sheet and do this as needed. You could wind up with a situation where it's 1 to 1, 1 to 2. So this will be the assignment you can now complete, showing how ionic compounds are formed. That is, elements that give up or receive an electron, so they become ions at the moment they interact.